management. So today I am going to present a lecture on stability analysis of slopes by GeoStudio. This is one software package to design the slopes for embankments or cuttings. So I will briefly discuss regarding this. After completing the discussion, I will just demonstrate a simple problem, how to calculate the factor of safety and how we have to analyze the stresses and everything. So after by concluding that, I will close my session. Yeah, thank you, sir.
Yes, sir.
So this is our department vision and mission. To produce high competent ethical civil engineering professionals with globally perspectives for catering to local, national and global needs, and evolving the department to provide state-of-the-art consultancy, research and development in the field of civil engineering and its allied areas. So coming to the mission, we produce high caliber civil engineers by providing rigorous hands-on education and practice with innovative and original thinking in the minds of budding engineers to face the challenges of the future. With continuous interaction of industries, research organizations and eminent professionals enriching the curriculum and setting the department as center of excellence for academics, consultancies and research in the field of civil engineering and allied areas. So by inculcating the field activities, we conduct some certificate programs, professional and ethical values to our students in order to make them prepared to face the competitive world. So these are the vision and the mission of our civil department. So coming to the today's topic, just these are the contents what we are going to cover in this half an hour subject. So first we give briefly about the slopes, what are the types of slopes and what are the failures occurs in the slopes and what are the methods involved to design to make the slope is safe, and a small introduction about the GeoStudio package and one small problem using that GeoStudio. I preferred here to design that slope in slope W. Right? So coming to the introduction, generally the slope is an unsupported or inclined surface of a soil mass. That earth slopes are formed for generally railway formations, highways, embankments, earth dams, canal banks, levees, and many other locations. Generally, they are the man-made slopes. So, of course, we have some natural slopes also. So here you can identify the man-made slopes. One is a ghat section, side of mountain. So here it is a anicut, we can say, or bund, we can say, for the tank, right? For the inspection and everything, we can simply construct a bund, right? So these are all slope structures. So we have to design this one as per the engineering perspective. So generally the slopes will occur by the slide of a soil mass, right? So generally the slopes will fail by a slide of soil mass. So here generally some gravitational forces and some seepage forces will act as the failure mechanism to fail that slopes or embankments. So these are the general failure patterns. One is the rotational failure and translational failure, compound failure, wedge failure, and some miscellaneous failures are there. So here you can observe in the bottom diagram, in the rotational failure, we have some slope failure by rotational slide and toe failure, base failure. So here you can identify a translational failure because there huge mass of the soil is sliding on the earth surface. So here you can identify a compound failure, some of the embankment and the base soils, they are failing in the any monsoon season or some dynamic pressures occurred in the crust of the soil mass. So here in the bottom diagram, we can clearly identify the wedge failure. A huge mass of the soil is coming onto the road pavement. So we can see so many vehicles are damaged, right? So due to the huge weight of soil coming on that pavement, right? These are some of failures. You can identify clearly here what happening in the translational slide and the rotational slide. So in the first picture, the huge soil mass is failing on the top of the bedrock, right? So huge mass of the soil is failing on the top of the bedrock. But in the second diagram, you can see the huge mass of the soil is fail in the embankment and they are coming out to the free face, right? So these are the general phenomena what happening when the embankment fails. So these are the methods involved in the design of slopes. Pullman's method is there, phi equal to 0 analysis, friction circle method, and Swedish circle method, Bishop's simplified method, Spencer's method, and stability charts, Morgenstern and Price method, Bell's method, some Cousins charts. So coming to today's topic, so I will solve a problem by using Bishop's simplified method. Right? So these are the methods generally what involved in the design of slope. So coming to this package, that GeoStudio, it is a modeling software for geoengineers and some earth scientists. So it is a rigorous analytical capability this software is having, and it is a sophisticated product integration, broad application to diverse geoengineering and earth science problems, right? So many of the geotechnical engineers and earth scientists, they are preferring this GeoStudio to analyze some soil problems, right? So in that, generally it involves the combined geometries and analysis in a single project, and draw geometry directly or import some CAD files. So solve multiple analysis simultaneously and interpret results with visualization and graphs, right? So generally we can expect the output, or we can give the input for this software in these 4 formats, right? The GeoStudio, the solutions it gives for the dams and levees, reinforced walls and slopes, excavations and open pit mines, roads, bridges and embankments, environmental protection, groundwater, ground freezing and climate changes, earthquake deformations, and Vadose zone hydrology, right? So these are the solutions generally the GeoStudio is performing. And these are the packages which GeoStudio supplies, Slope W plus SIP 3D, that's Sigma W, and Quake W, Temp W plus Temp 3D, Air W, and Cran W, Build 3D. So these are the some packages what involved in the geotechnical engineering and some earth sciences. So overall around 100 countries, they are using this GeoStudio, right? It is highly or widely used package in the design of geotechnical engineering. Right? So these are the general topics I will discuss in the Slope W in the design of stability analysis of soil. So I discuss about definition. So generally the definition, it involves set of the properties of the soil. Right? In the definition, generally we set the properties of that soil or materials, and in that again the basic analysis of properties will drawing in the model geometry, selecting the basic analysis properties and drawing the model geometry, creating and assigning the material properties, defining the trial slope surfaces, and establishing the pore water pressure conditions. So these things we will discuss in the definition. So So analysis part, already we discussed what are the methods we follow to design the slope. So in that Bishop's method is there. I taken this Bishop's method to analyze that slope, and I taking the multiple properties. In the diagram you can see I taken two types of soil layers, and I am following the entry and exit method to determine the slip surface, and we are applying some groundwater tables in the embankment, right? These three we are implementing in the analysis part. So coming to the solve manager, we use the solve manager to solve the numerical analysis, right? So we are just giving the elements, what are the properties of the soil and how the groundwater table varies from the upstream to downstream. So by giving that physical parameters, we analyze the total problem in the numerical analysis. And coming to the result point of view, we interpret the solve analysis in result view. So these things generally happened in the analysis point. So here why I taken the Bishop's method is, it is the minimum factor of safety and critical slope surface I am going to assume here. So as I said, we are taking two soil parameters according to the Moore-Coulomb criterion. So C5 soil I am taking here, and we are implementing to fix the critical slip here exit entry and exit condition I am taking to analyze, right? So now I will just go for the software and how we will design that slope. So sir, the screen is visible, sir?
Yeah, it's not, sir. Still.
Yes, yes, sir. I will come out and I will present once again.
Yes. Is it okay, sir?
Yes, sir. Is it okay?
Yes, visible.
So now, sir, is it visible now?
GeoStudio.
Yes, sir. Yes, sir. GeoStudio.
Yeah.
So here, as usual, to start any program, so we have to go for the selection of new. So in the new, we have to check whether the units, what units we are going to use. So here I am using the metric system, and I am selecting the output file in the A4 size format. So I have to take the printout, or I have to submit any report to the concerned client. So I have to show that in the form of a printed document. So for the printed document, I taken here the A4 sheet, right? So simply I'm going to create. So now dialog box is open for define the project. So here I'm going to define a project in the 2-dimensional, and in the 2-dimensional I am taking a slope W analysis in limit equilibrium conditions, right? So because all the things we are now doing in the limit equilibrium conditions. So here the name of that work, what I am going to give is slope stability for training. Just I am giving this one. And coming to the analysis type, so here so many analyses are there: Morgenstern price analysis, Spencer's analysis, Bishop, Jumbo, ordinary, sigma W, and Quake W Newmark deformation. So I am taking Bishop's method. So in that I am considering in settings here I am taking the piezometric line, because we said in the first lines, I am taking the groundwater line, that piezometric line in the embankment. So because of that, I am considering the piezometric line, right? So here the unit weight of water, it is standardized 9.807 kilonewton per meter cube. And going to the slip surface, so I am choosing the embankment will start at from left to right, or you can choose right to left, or use passive mode. The three conditions are there. So for this point, I am taking the structure will start at left and end at right, right? And slip surface option, I am taking the entry and exit condition. So where the embankment or the slip surface has to start and where to end, that will decide by entry and exit command. So I'm taking here entry and exit, and I am taking the structure from left to right. Right? So coming to the distribution, so I am taking the constants because the factor of safety distribution is constant. So generally the factor of safety will depend so many parameters like the shear strength of that particular soil, or friction angle, or height of the embankment. So like that, we design the factor of safety. So here I am taking the constant. So of course, it gives a critical factor of safety. After designing, so it will give the critical factor of safety. And in the advanced section, I'm keeping the numbers what they generally given. The minimum slip surface depth is 0.1 meter. So number of slices, I am fixing it is up to 30. So factor of safety converging settings, their maximum number of iterations I am giving for this program is 100, or you may change, no problem in that. So the tolerable difference in factor of safety is I am taking the more efficiency. So that's why here it is 0.001, or you may change, no problem in that. Right? So simply I am closing. Now the working window is displayed. So here the X and Y coordinates or axis, we can see the red axis, it will define the length of that embankment, and the green line, it identifies the height or Y direction of the embankment. Right. So here first I will check again what are the units. So going for the wave and check the units. So all are in mass, okay, in the kgs. So force in kilonewton, energy in the kilojoules, length in meters, so time in seconds, temperature in degrees centigrade. So okay, no problem. So we are in the SI system only. And coming to the axis, here sketch, I am going and I am fixing the axis. Here we can fix the structure. So what is the length and what is the height, right? To draw the structure, we need a dimension factor. So here I am taking the maximum x-axis is I am taking as 50 meters, and maximum y is 20 meters, right? So maximum x-axis is 50 and the maximum y-axis is 20. So here I need to scale the difference between the 10 and 20. So I am taking the minimum spacing. It is 1 meter. So 1 meter distance or 2 meters distance I am going to give. So I will take 2 meters, or I will take 5 meters spacing. So here it is 1 meter unit in the y direction I am taking. So here it is clearly visible. So what is the x and y? So it is x is a distance, y is the elevation. So in this x and y distance and elevation grid, so we will try to fix the embankment, right? So first I will go to the sketch line command to draw the rough diagram of that embankment. So just I will move the cursor to fix the lines. So 8 meters I taken the bottom layer, and 15 meters, and coming to 25 meters is a downslope, and of course 33 meters, and it ended here, right? So this is the lower layer of the soil, and again I have to go for the upper layer because we taken two different layers. So from 8 to 4 meters means 12 meters I taken. So up to 8 meters, the embankment is a horizontal line, and I met with the lower embankment surface, right? So this is the typical embankment structure, right? Now we have to fix the boundaries. Just now we planned the outer line of the embankment. Now I have to fix the geometry. So for that, what I am going to do is I am going for draw command. So I'm taking the region. So here, because it is not a circular or polygonal, so here we are taking the polygonal command because it is a domain region. So just I am selecting the lines what we earlier drawn. So lower part of the structure is finished, and again we are taking a second part. So this is the second layer, means upper layer. So you can identify numbers in this, number 1 and number 2, right? So here you can identify the number 1, number 2, because they are the identifications for the soil layers what we drawn. The number 1 represents the lower layer, number 2 represents the top layer. So here now we have to design, or we have to assign the materials, what type of soils we considered here. So I'm going to define the material. So define, go for the materials. So here I am taking the add command. So here there is a new material name is there. So I'm simply changing as lower soil layer. For the lower soil layer, I am giving some material properties according to the Moore column theory. So unit weight is 18 kilonewton per meter cube, and caution around 10 kilonewton per meter square, and phi is 25 degrees. So this is the lower soil layer properties. Now again there is a second layer is there. So just I am going for the same command add, but what I am doing is I am simply cloning the property. So what earlier it was given, right? Just I am simply changing the name. It is the upper soil layer. So I am rechanging the properties. For the upper soil, it is 15 kilonewton per meter cube unit weight. Coming to the caution, it is 6 kilonewton meter square. Coming to the angle of internal friction, it is 20 degrees. Right? So simply, I am closing now. Next, we have to add what are the materials we considered for this upper and lower layers. So for that, go for the draw command and go for material. So here there is a dialog box which showing the lower layer and upper soil layer. So we have to assign this one. So a lower soil layer is there. So just I am selecting this one. I am assigning here. So now you see the color of that particular soil is changed because the soil is, or the soil property is assigned for that particular portion. Now I am taking this second one, that is upper soil layer, and I am selecting the second part. Now it is assigned to the second part of that particular soil layer. Okay. So next, we have to give the piezometric line because some groundwater or water table is there in the embankment. So for that, we will go for the define, and we will give the pour that piezometric line. So in the define command, here there is a pour water pressure. So piezometric line is there. You just simply add by using command. So here XY coordinates are open. You just give the XY coordinates from where to where the piezometric line is falling down from upstream to downstream means. So here I am giving the X is 0 for always, and Y is 10. This is the first, the starting of the piezometric line, and I am continuously going for X is 16 and Y is 6. So you can observe the red line, red dotted line is visible in the embankment, right? That is the piezometer line. So 24, 4 and 44. So here you can identify the red dotted line. This indicates the piezometric line. Means if we consider this is the upstream side and this is the downstream side, the seepage is coming through 10 meter elevation to 4 meter elevation in the downstream side. Of course, the embankment is submerged in the downstream side, right? So we can we can simply by giving the coordinates, we can we can draw the piezometer line. So here we have to remember, so there is a water table we introduced in the embankment, so there is no need to give the unit weight or the pressure due to the water or hydrostatic pressure, because it is automatically induced in the analysis, right? So there is no need to assign again the pressure of water or hydrostatic pressures, because it is already induced automatically in the analysis. Now we have to check whether the structure is given the properties are assigned clearly or not. We can identify. So here you can see green arrows. This is the at top level 12 meters. Here in down you can observe at 2 meters, right? So these green triangles will tell the starting and the ending point of that particular embankments, right? So starting and ending point. So this is towards the right. So this is the starting point and this is the ending point of that embankment. Now we have to determine the slip surface. So where the soil fails due to its due to the external forces or internal forces which are developing in the soil mass. So that one we have to observe. So for that identification of the failure of the slip, so here we will use the command that what we discussed earlier, the entry and the exit, right? So that command we will implement to identify the slip. So for that, again, we are going to use the draw command. In the draw command, there is a slip surface function. So in that, there is a command called entry and exit, right? So simply you can see here, there is a coordinates XY, right? So entry range in the left side and exit range in the right side is there. So you can give the coordinates, or you just simply click the cursor on the top surface and you may drag. So here I am just clicking the top surface. I am dragging. So you can identify a pink line which is divided in between from 1.113 meters to 12 meters, right? So here it is 7 meters. So this is the range in the upside. So in the downstream also I am doing the same thing. So just I am simply dragging the cursor at the entry level and exit level. So it defines where the slip surface may fail, or how many number of trial slip surfaces will occur in that particular region. Or you can go for just giving some coordinates. In the X, you can go for 0, no problem. So where it is ending up to 6 meters or 7 meters, because the total length of the embankment is 8 meters on the top. Width of the embankment is 8 meters. Coming to the bottom, so it is again 8 meters width in the downstream also, right? So, but you have to go for the cumulative dimensions. So don't give limited values. You have to consider here the cumulative values, right? So now I have to check whether these functions are clearly I applied to the structure or not. We have to check that one. So for that, what I am going to do is we'll go for the solve manager. So in that, we can identify whether all parameters are implemented to that particular structure or it may not. So when you are going for the solve manager, if you are giving all the parameters exactly clearly, the solve manager will give the output, or otherwise it gives some statements you have to reassign, or you have to correct some properties. So according to the suggestions and warnings what they display, you have to redesign that or reconstruct that embankment. So here I am going for the solve manager by clicking the start command. So it is asking whether you have to save the file or not. Yes, we have to save the file because we need the output. So I am giving here a title. It is a training on GeoStudio. So where this file is going to save means we can select any path, whether it is generally by default it goes to the documents, or you can change, you can save in any drive, no problem in that. For the sake, I am just clicking in the documents only. So it will take some time because the total thing has to be done, but it has to run the program, and finally it will displace. Yes, yeah. Now the picture is came. So we given a 30 slices. So here you can observe clearly the white line will represent the critical slip plane. By default, it will give the critical slip plane. Why? Because here it is automatically selected. So we given this command, show the auto select critical. So because of that, here we directly identify a critical slip surface, right? So for this critical surface, the factor of safety is 1.221, or you can identify. So anywhere, so this is the 318 slip number. So this also 274 slip number. So 278, like this, we will get a number of slip planes. In that slip planes, we identified only the critical slip plane where the soil fails clearly, right? So the factor of safety at that plane is 1.221, right? So this is the stability of slope, but we have to identify the stresses. What are the stresses between the slice, right? So we can identify by clicking this select slip surface, right? We can go for this command, right? Free body diagram. So this is the free body diagram for the slice number. Here we can identify the slice number. Yeah, here it is moving. So this is the second slice from top, right? So here there is a dotted line, you can clearly observe. So here it is, we selected this slice, right? So coming to the third one, so this is the second slice, the free body diagram for this, the horizontal stresses and the resultant and the force diagram. So what are the shear forces, what are the resultant forces, and what is the phi, and what is the factor of safety, the critical factor of safety for that slip, right? So everything we can get this data here, right? This is the free body diagram. So finally, if we have to submit the report to the client, so then we have to go for save the file again. So I'm closing this free body diagram. So we have to generate a report. So here to generate the report, So there is a command like report, view report. So this view report generally we will get in the form of a HTML file. So we can, of course, we can save by taking some parameter, some data into the Excel and Word document. So whatever the requirement according to the client. So we will take. So here we are going to save in the HTML file. So this is the output file for that slip surface. So this is the data or file information. So when we started and for the client, everything we can give here, and the project setting. So these are the analysis setting, and means whatever the data we given input for that particular slope. So the data will be available in the analysis and materials. So coming to the slip surface, it generally displays the geometry of that particular embankment. So where we started the entry and exit. And slip surface limits, the left coordinate is 0, 12, and the right coordinate it is 33, 2. Means the height of that particular structure and in upstream and downstream. So generally we applied some piezometric line, means that groundwater line we can say. So the coordinates of that particular piezometric line also it will play, and what are the geometry conditions we went for. So here we went for 2D geometry. So these are the coordinates for the embankment. So these are the soil layers and what are the areas of that particular soil layer. So slip result, generally the slip surface analyzed 243 of 405 converged, right? So overall 405 slip surfaces are there, right? So here the current slip surface means the critical slip surface is 228, that is the number. So factor of safety for that critical slip surface is 1.221. Volume of that failure soil mass and weight. So what is the resisting moment and activating moment in that? So slip rank, it is from 1 to 405 slips, it is analyzed, and exit and entries, radius of that slip surface, and center, right? So these are the slip slices. We considered maximum 30. So, but there is a small portion left. That's why it taken 31 slices. For each slice, that X and Y coordinates given, the pore water pressure. So from where to where it is traveling from up to downstream side, the frictional strength and cohesive strength and suction strength, and finally the base material. So according to the pore pressure, this piezometric line. So here we will get from upper soil to the lower soil. Again, the slice numbers also it is from upper layer to lower layer, right? So this is the general design of a simple slope. If you have any doubt regarding this analysis, how we have to give the soil properties and what are the theories generally we applied or implement in the design of slope stability. So if anyone having any issues regarding this, you can mail me or you just post the comments to the Dean CRI. I will discuss all the doubts and clarifications in that. Right? So,
Okay,
Narayan, sir.
sir.
Yes, sir. Thank you, sir. Yeah, please, sir.
Can
sir. Yeah.
Yes.
Yeah.
Yes, sir. Any doubts from the participants, you can ask to today's resource person, Suresh, sir.
Sir, if anything is there.
Yes, sir. The students, they can come and so they can do their internships, sir.
Yes, sir. Yes,
very
sir.
nice
For that
platform.
point only, I discussed because this
nice
pandemic
platform.
time.
The students, especially first year, second year, any students, so they can come and 3-4 members. They can come and learn first the GeoStudio, and they can do a small work. Yes, sir.
Because this pandemic situation, it is very difficult to do the projects or internships in the college.
But online you can
Online,
guide, sir.
no
It's
problem,
free of
sir.
cost. Yeah.
Yes, sir. Yes, sir.
Yes. The students, it's a good opportunity. We can so interact with Suresh Praveen Kumar sir is available in the department. So you can do your internship. So you can claim the same in the department also. So it's a good opportunity. So thank you very much, sir.
Thank you, sir. Thank you, sir.
Okay, sir.
So
Kizar,
once
sir? Yeah.
Yes,
Go
sir.
ahead.
Yes, sir. Thank you, sir. So I
Sir.
thanks to Sri Suresh Praveen Kumar sir for sharing his knowledge with our participants. Okay, sir. Thank you, sir. Thank you very much.
Thank you, sir. Thank you once again, sir. Thank you for the
Yes.
CRI people for giving this opportunity. So thank you very much, sir.
Thank you for all the
Suresh sir,
participants.
for your
Yes, sir.
valuable lecture in this
Sir,
session.
thank you. Thank you, sir.
Regarding GeoStudio.
Thank you,
Yes.
sir.
Okay. I request all the participants, please assemble tomorrow. Yeah.
At same time, 7 o'clock.
Yes. Okay.
Okay, thank you.
Can I wind up, sir? Can I leave?
Yes, sir. You
Sir.
can
Yeah. Thank you, sir. Thank you.